two. One, so polynomial functions and rates of change. So when you get into advanced functions, you know, this topic of rates of change, so things changing with respect to one quantity, kind of comes up on a continuous basis. Now, you don't really have a huge amounts of applications in advanced functions with this, but you certainly do use rates of change in numerous scientific applications. I mean, engineering, definitely, you know, you'll see it in health sciences, business, and so on. And this rates of change I have gone over. You know, there's a full chapter in advanced functions. I can put up a link up above there to, for instance, one of the videos on rates of change. Now, in this video, you know, because it's a chapter just on polynomials, we can define rates of change exactly the same way. It actually never really changes for us. It's kind of like the transformations with parent functions. You know, you do the same thing, just your parent function changes. So for this topic on rates of change, you know, if you have, in this, I'm assuming that it's a polynomial, so your function is a polynomial, and because it's a polynomial, it's superly well behaved. You know, there isn't anything to worry about. You know, it's not always very easy to graph, especially if it's a higher order polynomial, but the lower order polynomials, okay, in terms of like a quadratic or cubic, are relatively simple. Okay, now with these polynomials, if you want to be able to calculate the rate of change, so if you remember, there's kind of the average rate of change. So, you know, what happens on a particular set, okay, and typically what you might be calculating is kind of like a secant, right, which is basically just the slope of a line between 2 points that are on the function. So if you have, for instance, you know, let me just switch here the color. So if you have one input, okay, you're going to obviously get an output out, okay, so let's say that would be your point number 1, which is going to be x1 with the output y1, so that's one ordered pair. And then, you know, we can certainly put in another, and that's going to create our second output. So let's say point number 2, and you would have x2, and then your corresponding output y2. Okay, so this is what we have. So p1 and then p2. Great. Now, if you want to talk about kind of the average rate of change, okay, or the secant between those, you know, wherever those two things are landing. So if we had, okay, our y-axis, okay, and our x-axis, you know, and then here's our function, you know, let's say it's because it's a polynomial, so I'll just kind of graph it like a polynomial. And let's say this was x1 right here, and I don't know, you know, let's say this was your x2 right there. So now if you wanted to find the secant, all you're really doing is, you know, you're connecting this and you're just finding the slope, and that's not a big deal. So we know that slope is the rise, okay, that we have, and then it's over the run, okay, which is in this direction. So it's going to have a positive slope of some particular value, right? So again, so this is delta y, so the change in y over the change in x, which is just rise over run, and this is our old school slope. So that's not a big deal. Now, so that's for secants, okay, that we are going to be able to find. And, you know, so for these average ones, put up a link up above there, you know, you can review that concept again for these polynomials. Now, with respect to an instantaneous rates of change, so we still had the same definition, right? So we still had, okay, the change over y and the change over x. But instantaneous basically meant that these 2 points, so this x1 and x2, okay, so these inputs, we're just getting closer and closer and closer together. So, you know, if we kept moving this x2 and we kept, you know, shifting it here and then here, okay, and here and then here and here and here and here, you know, and eventually, you know, we're going to get as close as possible so that these 2 points right there are going to be coming closer and closer and closer together, okay? And that was kind of the tangent line at a particular point, which is the rate of change, okay? And we refer to as an instantaneous rate of change, as this difference between the 2 points basically shrinks to 0. And that was defined like this for instantaneous rate of change. Let me copy this and I'll bring it down. So we had it, okay, for some point A, you know, so it could have been x1 or x2, but it's just some point a. Okay, so our function, so this is like our y2 minus our y1, and then our change in the x was basically becoming extremely small. Okay, and for that small, we refer this to as h. Okay, and that is the kind of the difference in between. So this came from, okay, because it was a plus h, so that was kind of like x1, and then x2. Okay, what we have, okay, in this particular case, it could have been just an a. And when you subtract the two, okay, you're going to get a difference of just h, because the a's will just cancel. All right. Now, it doesn't matter if it's both positive or negative, okay, the h. So it's kind of coming from both sides and it's shrinking towards 0. Okay, so that's what this means. H is just getting smaller and smaller and smaller. And in calculus, we call this, the limit goes to 0, okay, as you becoming. So that was my instantaneous rate of change. For polynomials, it turns out that you have an instantaneous rate of change. So you can have these tangents anywhere. They're very well behaved, so you can basically find the instantaneous rate of change at any point. Now, assuming that the domain has been the entire x-axis. And once you have that, okay, once you can pick a particular point, you can find the instantaneous rate of change, and off you go. Now, if you're asked to find the average rate of change and you're doing the secants, no big deal. You have done slopes over and over, starting probably in elementary school, and then you've done it in grade 9 and 10 and so on. All right. So let's do an example with a polynomial, okay, just kind of as a refresher to these rates of change that we would have, and kind of I'll do it for an instantaneous rate of change. So let's say, so here's an example, and we're going to pick, okay, x is equal to 0, so meaning our a for our definition. So if I would, let's say, paste this back in here, so our a is going to be 0, and we're going to make h as small as possible. And you can pick any polynomial you like, all right? And an instantaneous rate of change at any point, and you can always find it. Now, one thing I will mention for you as a student when you're doing these rates of change, there's something which is really nice that happens, and that is there's kind of these maximums or minimums, okay? So most of the time they're local for polynomials that you would have. And at those particular points, our instantaneous rates of change was 0, right? Because it was a changing of the tangent, and you may remember that from those local max and mins. I'll put up a link up above there as a refresher if you like, okay? So in summary, for polynomials, you can do any rate of change that you like. I mean, polynomials are nice as possible in terms of functions. And you can use the same definitions for instantaneous rate of change. Obviously, let's knock out this example so that it kind of refreshes you, and then you can try some examples on your own. All right? Okay, so for this, so what I'm going to do, so from right here, kind of going to do it in, fast forward fashion, but I just want to write it out for you. So I'm going to put f. Okay, my a is 0. Okay, I'll put up an h in there, and this is going to be minus f again at 0. So that's the point that I've chosen. You could have chosen any point. And then my h in this case, and that's my instantaneous rate of change. Okay, and we're going to try to make h as small as possible. All right, both from the positive and negative. And let's see what we get. So let me plug this into our polynomial, and then we're going to simplify it. All right, so here we go. I'm going to just change the color. So we're going to get, so first, so this is going to be 3, okay, multiplied by, so that's that. I apologize here. Let me erase this because there's an h there. So let's substitute that. Minus, okay, 0 plus my h plus 5. Okay, so that's this right here. And now we're subtracting. And now we're subtracting. We're just subbing in 0. So if we substitute this, that's going to be 0 minus 0. So that's going to be just 5. And then divided by, okay, my h. All right. Now it is annoying because, notice this is cubed. So the bigger polynomials, it becomes a little bit of a headache because you have to kind of expand the entire thing. Now I did substitute it for a is equal to 0, so really we just have h cubed. So that's not a big point. But if a was, let's say, 1 or minus 1, you know, and then you're going to be expanding, okay? And if it's to the cubed or to the fourth or to the fifth, you know, it's going to take you a little bit of time. Okay, so here I'm going to get 3. This is going to be h cubed minus, I guess, h plus 5 minus 5 all over. All right, h equals. So here we have, okay, so this is going to be 5 minus 5, so that's gone. And I have 3h cubed minus h all over h. Okay, now simplifying this, so this is going to be 3h squared minus 1 equals. Okay, so that's what we have there. And now notice right here, as you make h smaller and smaller and smaller, what happens to this term? Well, this term will disappear on you, right? Because h is going to be very, very tiny. You're going to square it, so it's going to be a very tiny number. So let's say if I put 3 multiplied, and let's make h, you know, very small. Let's say something like this, and we square it. Notice you're going to get 3 times 10 to the negative 14. Okay, from scientific notation. So that's a very tiny number. So really what's happening is that this is approaching -1. So that's my instantaneous rate of change. Now, is it always going to be this nice for polynomials? It turns out yes. Okay, the only thing is that this expansion, so these expansions of the polynomials are a little bit annoying, but you can certainly do them, go all the way through. And then once you do those, you can actually cancel off. So this h is going to be canceling things off for you as you keep going. And then you can find out what your actual instantaneous rate of change, or the slope of the tangent line, if you remember, because that's what it is. Now this was at 0. So basically our slope or instantaneous rate of change is about -1. So it's kind of, you know, this way. So it's, you know, our slope is going to be like that. And, you know, if we would do this, if I would plug it back into Desmos. All right, so here we are. So here's Desmos. I'm going to just plug this in. So it's going to be 3x. So right here, so 3x cubed, and it's minus x plus 5. Right, so this is what we have. We wanted it at 0. Okay, so it's basically at this point. So it's 0, 5. And notice that, you know, if we kind of zoom in here around there, so notice our slope, which makes sense. It should have been around -1. Okay, so that's what we have. That's what we've just found, the instantaneous rate of change. And you could have done that for anything. And now, of course, so notice in here, so at that particular, so that would have been your local maximum, and this would have been your local minimum. At those points, the instantaneous rate of change would have been 0 for these. And for polynomials, it's always the same, right? So you always kind of go through this process. I do encourage you, you can take even the same function, find it for, let's say, you can actually find it for that 0.333, so I guess for 1/3, right? So x is equal to 1/3. And see that you get a slope of 0, right? That would have been a local minimum there. Or for -1/3, again, you would have gotten 0. Or you could pick any point that you like. All right. Okay, that's it for this video. And it kind of finishes off these polynomials and then relates them back into rates of change again for you. Okay, ciao everybody. Peace.